can you do with 96 nibbles? Okay. That's the game of Tron. Blue score lives. Libby, move cycle. Oh boy. Angus. To crash. The scorekeeper. Okay, that's how it's done. Okay, so these are pseudo-random dice. Got 3 5s. I got 19. Oh, nice. Okay, this is one of the most important programs in this kit, and I'm just going to run it. And what it is, it's electric dice. So what you're seeing here are the addresses of the code it's executing and the value of the dice. And when you hold down a key, it freezes it at that number. And then any key will freeze it. So here we're generating real random numbers because they're based on user timing. Okay, and I'll stop it. Now this is the code that makes that happen. So it starts with an 8 in address 0, and an 8 means transfer into A. So we're going to transfer a number, and the number is 1, so that starts in our A register. And then number 1 is the opcode for AO, which outputs the value of A onto the hex LED. Okay, we increment, see the next address. Okay, 2 is a CH, which means exchange the registers A and B. So that 1 is going to move into the B register. It's going to swap. Okay, and now there's a 0, which means check the keyboard, and then the following instructions determine what to do if a key is not pressed or if a key is pressed. So the next instruction is an F, which is a jump. So if a key is not being pressed, it's going to jump to 0B, where the program will continue. But if a key is being pressed, it's going to jump to 1-6. So let's take a look at 1-6. So you put 1-6 address set, and it shows you the value at that address. And that's the 1, and that's the 6, 4, and 2. Okay, so there's a 0, which means KA, to get the value of the keyboard, see if a key is being pressed or not. So if there is no key being pressed, we're going to jump to 0-0. So we're going to continue the program if we've released the key that was being pressed. But if we're still holding the key, F1-6, we're going to stay in a tight loop until the user releases the key. So let's go back and find where we left off. Okay, here was the jump to 16, 1-6 hex. Now we go to a 2, which is a change, which is going to restore the saved value of the accumulator from earlier. And then we have a 9, which means add into A. So the next byte, next nibble, is what we're adding. We're adding a 10. So A is decimal 10. So like if we had a 1, we're going to have an 11. And then if there's a carry or not. So if there is no carry, we're going to jump to 0, 0. Okay, but if there is a carry, we're going to add 7. So 10 plus 7 is 17. So if we've overflown the F in our add, then we're going to add the 7, and that'll essentially wrap it around. So it's like adding 1 in a sneaky way without having to check your boundary from 1 to 6. All right, so then F02 will jump back to address 2. And then here is that 1.6 address that we looked at earlier. So let's go back to 2, and that is the 1, which is the A output. All right, so that is the Nibble code for the electric dice. And when you run it, that's what you get. So these are real random numbers because they're based on user timing. Now, you may have had some programs where you have to move your mouse or mash the keyboard in order to generate entropy. That's exactly what this program is doing. It's simulating, it's really using user timing to generate true random numbers. If you're calling like a random function in a programming language, that's using pseudo-random numbers. So what that does is uses an equation to figure out what next random number should be. So if you're doing that, you want to seed the random number generator at the beginning with some random value, like timing the user's time before they press the return key or something like that. So it's an important lesson because you're learning that pseudo-random numbers are not true random numbers. And if you really need true randomness, you need user input. Let's take a look at an integer basic program in Micromate. Let's load TTT for tic-tac-toe. And here is the listing of it. And run it. Okay, we're playing tic-tac-toe for Bitcoin. It's worth 1561. So let's move X, picks 1. Bitcoin changes every move. Okay, what will O do? O will go to 5. All right, X will go to 2. O will go to 3. X will go to 7. Blocking. O will go to 4. X will go to 6. And O will go to 9, and X will go to 8. And nobody won Bitcoin in that game. So let's see what happens when they win. If X wins, let's see, 1, O goes to 2, X goes to 5. O is stupid, he goes to 3, X goes to 9, and X won $2,600. The Bitcoin went up afterwards. So now we'll let O win. X will go to 1, O will go to 2, let's see, X will go to 3, O will go to 5, and X will be stupid, he'll go to 7, O will go to 8, and O should win 2,082 Bitcoins. All right, so we have competitive games and non-competitive games. So let's play another competitive game. 1, 2, 3, O goes to 5 to block. X goes to 8. O goes to 9. This is really exciting. X goes to 6. And O goes to 4. And X goes to 7. And nobody wins. Let's let O win. X goes to 1. O goes to 5. X goes to 2. O goes to 3. X goes to 7. X goes to 4. O goes to 7. O wins. So what would a cooperative game be? Well, if X and O realized that they could just raid all the money out of the bank just by taking turns winning, like our presidential election. Uh-oh. Okay, let's try that. X goes to 1. O goes to 2. X goes to 3. All right, so we could just let X win this time. Okay, O will go to 5. X will go to 4. O will be nice. O will go to 6 instead of winning. Let X win. Okay, now X is going to let O win. 2, 4, 5, 3, 8. Look, we're robbing the bank here. Now X will win. 3, 2, 6. Oh, 5. Okay, 6, 7. X won. Only $339, but oh well. Now we'll let O win. 2, 4, 5. Be stupid. Let O win. O won 2,000. All right. So now if O is nice, so let X catch up. 1, 2, 4, 5, 7. Okay. And then O is going to let X catch up again. This is a very boring game. It's not exciting because it's not competitive, but both sides are winning. 2, okay, 6, 5, 9. Look at that. We're almost caught up. Robbing the bank here. And let's go back to competitive. 3. O is 6. X is 9. O. 5. X 4. O goes to 2. X goes to 8. O goes to 1. And X goes to 7 and wins. Okay, so we're caught up. I was trying to be non-competitive, but I became non-competitive. All right, so let's play 6. And we're going to be non-competitive. 3. Okay. Okay, we want X to win. We're going to break the bank on X. $32,767 is the most that you can get. But do you understand the difference between competitive and non-competitive now? That if you both find a win-win, that you can both make out here. All right, let's try again. O winning. 2, 4, 5, and 9, 8. So O's going to win 2612, and we're very close. We've already pulled 30,000, almost 30,000 bucks from this bank. Because of these rules, we looked beyond the system and saw how we could both win in an abundant economy. Okay, so let's break the bank for O. Okay, 1, 2, 4, 5, 6, 8. 1, 2, 4, 5, 6, 8. 1, 2, 4, 5, 6, 8. 1, 2, 4, 5, 6, 8. So this pattern could continue. Yeah, you find that repeat the same pattern. Okay. No, I messed it up now. 3. Yeah, it became competitive again. Okay. Let's try to get them both up to the max. 1. Okay, so X is going to win a little bit. 2, 4, 5, 7, 8. Okay. 1, 5, 2, and 3, 7, and 9. Okay, 1. Boy, that competition capitalism comes right back at you. All right, you could play forever in competition and nobody wins. All right, 1, 2, 4, 5, 7. All right, 1, 2, 4, 5, 7. 1, 2, 4, 5, 7. All right. X broke the bank, but O didn't do too bad. Okay, so here's code, and there's the random function at random 5000 and integer basic gives you random numbers between 0 and 4999. So there are subroutines at 1000, 2000, and 3000. So 1000 is what draws the board. Call -936 clears the screen. This pound sign is a not equal in integer basic. And what you wind up having to do are statements like this, because the continuation after an if statement is not as many people would expect. So you do the opposite. If I is not equal 3, then jump here. And then here is what you do. You wanted these two statements to be executed if I equals 3. Okay. And then this is the logic that checks if there's a winner to the game. So it's just an array 1 through 9 of the tic-tac-toe board. And a 1 means X, a 2 is O. And it's just going through that logic. And to see if the game ended in a draw, you just check if all of them are non-zero. That means that every square has been filled. So have fun with integer basic and cooperation.
Christmas, we do Hanukkah.
How about Swedish?